It's now live.
Okay. So, good afternoon, everybody, and thank you for attending also to the keynote of this blockchain forum. In particular, today's keynote speaker will be Professor Burkhard Stiller, and his talk will be basically on the uses of blockchain for commercial processes and which pros and cons are present in that. Just to provide a brief introduction of Professor Stiller, he runs the Communication Systems Group at the Department of Informatics in the University of Zurich since 2004. And he previously holds the positions at the University of Karlsruhe in Germany, and also at the University of Cambridge in English, at the Swiss Federal Institute of Technology, ETH of Zurich in Switzerland, and at the University of Federal Armed Forces in Munich, Germany. Please, Burkhard, the floor is yours.
Thank you very much, Giovanni. Thanks for the invite. Hello, good afternoon, good evening, good morning, wherever you are in the world at this very moment. Welcome to the blockchain's world. And as you see probably in my virtual background, there are some Swiss mountains slightly contrasting the Sevilla type of very hot weather, although we have at the moment quite nice places as well. I would like to run through some basic blockchain viewpoints, initially giving you a fresh view on what blockchains do, and then try to address how business process management and IoT, thus commercial processes, can benefit or cannot benefit from blockchains, and these are the pros and cons at the end. So it will be a sort of discussion in that setting. Let me start by asking a very simple question, and that is, of course, in a remote setting, a bit more complicated than in the real life setting. Which gaps do blockchains close? And I will try to give you an answer on that one by looking in distributed systems, which we, I think, all do know. I will start off with something which many of the younger generations in this audience today probably have never heard of. The older ones do know those ones, which are the telegrams. These were physical objects where you could basically type in a message on a postal office, and the person at the counter would use a system to transfer that across wherever it had to go across the world, and would end up there being printed and then delivered to the destination. So these were physical objects for information transfer. The final and last one being sent in Europe was in Belgium, end of 2017, so only 2.5 years ago, basically. And we all know digitized representations of those ones exist as well, and these were the emails popping up in the mid-70s, including all the different attachments, so going well beyond the traditional ASCII type of text. Secondly, the digitization of society moved on when we did see the invention of Wikipedia in 2001, where all those larger dictionaries, here is a German version on Brockhaus, but it might be Webster's or Oxford, Cambridge dictionaries, with whatever number of volumes existed out there, were sort of moved from the physical world to digitized representation. I'm not judging the quality of Wikipedia, I'm just saying it's a digitized representation of a physical object. What are the commonalities between those two pillars? Well, those systems are operated in a decentralized fashion, which basically means we do have not a single point of control, and they are distributed systems at the same time. So you have at different locations in different places of the world a set of instances helping with multiple things in there. If we would use that type of society today, we could not run a full business. So that's why we are looking at something where you could have potentially a decentralized and distributed system as well, where money would see a replacement. And the question is, can we exchange a digitized representation of coins and bills in our decentralized world as of today? Yes, because in the 80s and 90s of the last millennium, we did see digitized e-gold and Linden dollars popping up. But the problem there was when you started spending money, you had to verify that a digitized representation was already in your possession, and you simply did not have the chance of cut and pasting a bit string and handing that out to Giovanni and Jose somebody else, and they would basically do double spending. So you always had to ask a central instance. That's why those systems were not decentralized, although they were distributed in that sense. They disappeared because at that point in time, society used credit cards, and credit cards became popular. You could use them in payment systems across the internet. So there was no need for that. That changed in times which you all know, I guess, end of 2008, early 2009, when Bitcoins came in. These are fully decentralized, distributed systems, which are called blockchains today, which made the money as a digitized representation fully decentralized and distributed and available. So society can work with all business processes in that sense in the fully digitized representation. Of course, I cannot still sell my tomatoes because I cannot digitize them in the very same quality to be edible at the end of the day, but in principle that could be working. Why did I do that introduction? Because we need to go back to processes. Not only business and management, but a little bit on the database first to understand why blockchains now have potentially seen a larger and wider spread use than just for cryptocurrencies, as they're typically termed in that setting of the Bitcoin case. The idea is to replace central databases, at least in real principle. So distributed ledgers shall help to replace the client's access protected rights to any authoritative database via validation rules, as we all know that from a traditional centralized database, by a distributed consensus of decentralized validators, here shown at the end, multiple ones, while the database state depends on the majority agreement of all of those validators at hand. So they find a consensus, and that's why the combination of those quote-unquote databases, the copies of the instances of those similar distributed ledgers have to be made available and accessible to everybody in the world. So that's why the distributed and decentralized database is a principle which is now replaced by potentially that ledger. But what is the difference now between a ledger and a blockchain? I will start off by initially saying that they are sort of similar, except for the fact that distributed ledgers are typically termed private blockchains and blockchains typically are termed public blockchains. While this first word might change a bit on which document you read, which publication you take a look into, and which media you follow. Both are able to maintain digital records of the so-called who owns what relation without a central storage. And that's the key. You have digital records which indicate that there is some sort of ownership at hand. And that makes it a little different compared to a database, because if I hold, let's say, my address entry with my name, my phone number, and my whatever email address, that doesn't really mean there's value attached to that. Well, be careful, value on data itself may change, but on the single entry, most likely it's not. So we have to have something else. That's why here value comes in the picture. To make it work, either in ledgers or blockchains, the consensus mechanism ensures then each of the copies of this ledger is identical to every other node's copy it holds. Not necessarily real time right now, but after a certain period of time, all the partners agree we have the same view on that. And this is important compared to databases as well. Databases typically show a real-time characteristic within a few seconds, typically affected by the situation of end-to-end delays of communications. In blockchains, that is not the case. It might go up to 1 hour, like in the Bitcoin blockchain, before that node's copy is identical to everybody's else. How to access? Well, reads and writes obviously are important. The write access to blockchain is done by miners, validators, or some other term, depending on the specifics of that blockchain, especially holding the data of that asset owner at hand, which shall be located in the blockchain. So these are those digital records with the who owns what relation. And we have then cryptographic signatures at hand. They are typically sort of costly to a certain extent. It's not easily done by everybody. And that's why miners get a reward in certain cases. The read access, in contrast, is at no cost and typically quite quick. You just ask the blockchain or ledger and get something out of it. By just having said that, our key advantages of, be careful, public blockchains are immutability, traceability, and preventing double spending, especially in the situation of our cryptographic currencies, obviously at hand. But those very simple ledgers and blockchains have already mutated. They are not identical as the ones we just saw in terms of Bitcoins from the early 2009s. We do see them as the sort of era one, where the proof of work principle was used to make sure that immutability is guaranteed. And we see in general roughly 6,500 different cryptocurrencies out there if you take a look at coinmarketcap.com. The second era started off with Ethereum, including smart contracts, a programming language besides regular languages we know of called Solidity, which helps to determine in which way we can write contracts that are executed on different positions of the world and then commonly agreed upon. And the era 3 was then the Satoshi Dai starting point, which is basically a very simple distributed game implemented in a decentralized app and a DApp and a DApp fashion in April 2012, where those systems are running on peer-to-peer networks with all the data transparent and being tamper-proof. So this is the third area, and we have seen the move beyond fintech applications with friendly web interfaces and all sorts of tools out there, which help to suddenly make out of those very specific applications a larger set of processes becoming available, which are then typically, I guess, placed in commercial processes for making business out of that. And this is the fourth era, starting off basically during the 2015, so roughly now 5 years old, where the blockchain's ecosystems popped up, where the industrial integration showed up, and many blockchain ledger projects in many different fields were coming along to ensure that we can make use of that. And only with those type of fourth era, we are able today to use blockchains in different processes, commercial ones besides the fintech domain as well. Note that those eras still run today in parallel. They are not sort of replacing each other. They do their job because we still have a digital currency in the Bitcoin. We have those projects out there, as I mentioned in the fourth area. But trying to get the real fundamentals into a very quick view, identifying that we have a common view of why we finally can rate the use of blockchains in commercial processes. The content of blockchains and ledgers are transactions, typically collected in blocks, and those blocks are created regularly. Here we see one of those with 2 transactions included. They carry a unique ID and a hash value, which is basically value of something which was placed inside the blockchain earlier. And then if you place a new block into that, you have to have a hash off and a pointer to the previous block, which is then the hashed pointer, basically. That's why it's called blockchain. Very simple, isn't it? And then what type of consensus is being run? I just take here the most secure one out there, the proof of work one, which solves crypto puzzles, basically partial hash collisions using SSH256, where you have to find a hash value of a given content of the block from the very first metadata to the last bit right here. And that hash shall follow this algorithm, but needs to show initially, let's say 8, 9, or 10 zeros. And finding those hashes just requires hashing power. You have to run that algorithm once again after the other one, adding besides the content a nonce, which is a randomly generated number, and trying it out. And whoever wins that crypto puzzle, so finding this partial hash collision with the number of zeros first, will win basically that game. So the creation of valid blocks is performed by everyone, by anyone, you, me, whoever likes to. So that's the incentive, because once you solve the cryptic puzzles, you have a chance of confirming the block for a given blockchain, and you do the mining, especially if the blockchain generates cryptocurrencies as a reward. And this approach is typically computationally expensive, and that divides double spending because you have no chance of readjusting those pointers, changing the transaction content right here of the past with a reasonable amount of energy as well as compute power. In Bitcoins, I think it's considered to be 6 blocks, basically an hour waiting time, and then there's almost no likelihood to really do that. So you cannot really spend the coin to Giovanni as well as Jose at the same time. After 1 hour, they can blame me, Burkhard, you did do something wrong because you tried to do that. So that will not work. In addition to that, as I mentioned, those blocks are just containing data. They're not really active. They're just very passive. And so smart contracts popped up to make processes much more effective and being able to deal with current situations, so have a chance of adding specific decisions. So here, not only data is part of a transaction, but smart contracts. Let's say the solidity case in Ethereum, that's a piece of code, if then else, do this following. And they can be executed and validated on every node's copy upon persisting that specific block. The Bitcoins do not have really a smart contract, although we have some calculations. That's a blockchain-based cryptocurrencies Bitcoin script language, because you only had to withdraw, escrow, refund, or transfer Bitcoin. So it's a very limited mathematical set of operations. So here we now move from passive data to active data. So that's why a blockchain in general, or a distributed ledger in general, are sort of active databases at hand. Those smart contracts are way older than blockchains, because Nick Szabo in 1996 already defined smart contracts as computerized transaction protocols, which minimize the need for trusted intermediaries. And I think that's the key element that you have. You can basically agree between Giovanni and me on some contract without asking a notary, without asking a third party, a trusted third party, and still both of us would have a chance to prove whatever we have said is according to the rules at hand. So smart contracts are unfortunately neither smart nor contract, nor a contract. The term is sort of misleading in that sense, because they just implement whatever you've written in Solidity. And they are not formally not contracts, because the legal side is not well defined depending on the specific country you are living in, because there are no terms and conditions attached to that. But they need an infrastructure, and the blockchain-based infrastructure is the ideal one because it is of distributed basis. There is no central point. You can distribute whatever you want to, and that's why you have a chance of working in there. So why are those transactions and smart contracts not helpful for business processes? Because those who owns what records are our assets. They're the digital assets to be sold, to be stored, to be safeguarded, to be bought, and they are electronic representations. That's why they are wonderfully accessible in our digitized world as a file. They might inherently bear the right for exclusive use. So if you have a certain ownership of a video stream, which you bought from a manufacturer of movies, then you might be able to run it. But there are a few other elements, what those who owns what records look like. That might be a token, typically refined as a digital token. So it's a digital asset, which is issued by a stakeholder giving the right to participate whenever you are part of that network of stakeholders. So it may allow for payments, quote unquote, inside that network. It may allow to handle those tokens internally. I typically use the example of the Boston T, the metro line in Boston, in the US. When you ever want to travel out, you have to buy beforehand an ATM vending machines, those tokens, which you drop into the entry gates and then they open and you can travel. They won't take US dollars. So you have in the digital work such tokens as well, which allow you for a given set of stakeholders to do payments. Obviously, that's restricted. That's why we need something else. And the coin or digital coin is then the generally defined electronic representation of value, which is specifically designed to represent money with a network of stakeholders typically participating in the blockchain and beyond. So like in the Bitcoin case, it's not only the miners participating in there, everybody collecting Bitcoins can use them for payment. And cryptographic mechanisms help to provide a sufficient large counterattack against counterfeiting and double spending to make the thing work in a fully decentralized setting and environment. Note that you can buy typically a token with a coin, but not vice versa, because the token is limited, the coin is more generally. Note that I place the word money here in quotation marks, because depending on the economic situation, money has a side effect of multiple regulatory constraints, which I'm not considering at that very moment. What are token types out there? Luckily, the FINMA looked into that point. FINMA is the Swiss regulator for financial transactions. And already in 2018, they defined 3 different types: the utility token, providing access to an application or service by means of a blockchain; the asset tokens, representing assets, either debt or an equity claim on the issue. So basically that promises a share in the future company earnings or future capital flows, whatever it might be. So it's sort of quite analog to equities, bonds, or derivatives in that setting. And we do have those payment tokens, which are used as a means of payment So they are basically the synonymous term for cryptocurrencies or a dedicated coin. And note between those two ones, we technically see no difference because it's a sequence of bits and bytes. But very important from the use, here they promise a share, and in payment tokens, the cryptocurrencies give no rise to claims on their issuer. So that's very important difference because the generation looks different and the use looks different in that sense as well. So far, I think we have a clear understanding of what we can talk about and exploit. We will not look into all the consensus mechanisms, Merkle trees, blocks, ingredients, transaction handling, etc. That doesn't matter at this point in time, but we need to be flat on the following distinction. And that's, to my mind and to our decisions, a very important thing to look into. The types and terminology in a quite simplified but straightforward manner on distributed ledgers and blockchains. We do have private permissioned instances. Sometimes you'll find the term enterprise grade distributed ledger as well, where the read, the write, and the consensus finding, those three elements I just mentioned beforehand, are restricted to an authorized set of nodes. They are predefined stakeholders, and if somebody decides to do those ones and to assign those ones, there is no chance from the outside to change them. So if Giovanna, Jose, and myself would decide to take us and we run a blockchain, then we might have an enterprise grade deal. Nobody else can participate in that sense. We are completely between ourselves. You can have that private permissionless, which basically means you move into a consortium grade where the read now is partially open. So we might open it up to everybody participating that very now at this moment for read access. So we have to trust our three people right here at that moment who write and find the right consensus all the time. But everybody in that webinar is forming the consortium and who have a partial read. And as I mentioned already, there is a trust issue in here. If you open it up to you attending, then you sort of have to have a certain level of trust with the three of us to indicate, well, probably what they do is okay. But if you don't trust them, the content will not be trusted at all. Thirdly, the public permissioned one is the type of situation where the right and consensus are restricted, as in the two other cases beforehand, but the read is open to everyone. So we have a very publicly accessible, worldwide accessible situation. That's typically the controlled collaborative term for that at hand, but nevertheless, the right and consensus for those who persist data in the chain, we still have the authorized assumptions. Those three elements of the distributed ledgers have very strict assumptions on the trust of those people who write and who perform the consensus. In contrast, and that's the open space, hopefully on that slide is here, is the public permissionless chain where read, write, and consensus is open to everyone. So everybody here on that webinar, plus everybody else in the world, which we select randomly, or which may decide to pop in, there's no need for selection at all, can do whatever he or she likes if they follow the process in terms of the protocol being specified. So there's no restrictions, and it's fully transparent to everybody participating. That's why it's really the public blockchain and the blockchain at all, because that is the term originally used by the Bitcoin case, where everybody can write and read without any pre-access controlled elements. And that's why here we have only the closed situation, partially open up on the read side. This is something which is becoming very important because the underlying trust assumptions are very different. And that's why commercial processes building on ledgers do still require from participants from the outside world to have that trust in those right and consensus finding nodes at hand. So is a business process management style a blockchain case? Well, it is, isn't it? I put an exclamation mark in here. And at the same time, I sort of question that and say, is that really a blockchain case? Are we always in the situation to say, yes, we can use business process management steps to make blockchains or ledgers work for us? Well, let's assume the following. And I know that there is a few different definitions of business process management out there, but I think it's commonly acceptable that we can consider BPM as a set of disciplines which use methods of discovery, modeling, analytically, investigating, measuring, improving, optimizing, and automating business processes. They are not specified in principle, but they should have an economic value. And that's why this who owns what relation of the blockchain beforehand becomes very important. If you take those different methods at hand. They vary very specifically on different commercial processes. Obviously, why would I need discovery, for instance, in the Bitcoin case? It's a process of generating cryptocurrency. Probably it's not really necessary. Why would I need to do measurement in cases where I have nothing which is being created newly, I just exchange data, for instance? So that's why this is a very high level, of course, assumption. But what is important is that those four methods at hand possibly impact blockchains and distributed ledgers use, because here we look in operations. This is more, quote unquote, the design, as well as sort of initial overall effect of how to build a system. Here we definitely have operation. That's where a blockchain probably can get hold of some interesting effects. One of those commercial processes we looked into are supply chain processes, which are typically sensor dependent. And that's why our Internet of Things world typically support those methods, because you can measure things, you can optimize things, you can automate elements as well. That's why I basically took the liberty to take our Swiss supply chain tracking system for dairy products, because we are originating in Switzerland. This was a project we jointly did between the Federal Office of Agriculture in Bern and ours, by looking at a supply chain tracking model. And now that's being used as a commercial process, because we have producers, all the different farmers. I think there are 20,000 in Switzerland herding cattle. And we have consumers roughly at 8.5 million. Well, babies don't go shopping, but like a little less than that. But everybody who's buying dairy products in there. So we have basically, due to this customer situation and the consumer situation, an unknown number of stakeholders out there. Everybody could potentially buy. If tourists come in, others come in, they may have a chance to buy. So what is the problem of having supply chain tracking at hand? We would like to make sure that there's, from the milk to the desk, in terms of milk, yogurt, or cheese, is sort of maintainable. And you can have transparency for all those steps. That I know this is milk out of the canton of Appenzell, and it delivers Appenzeller cheese and not Gruyere and something else. So we have regional products which can be distinguished by just indicating very clearly where they come from. And that's why, besides transparency, our tracking requirements need reliability. So whatever we collect in terms of data for such a commercial process must be reliable for the producers and for the consumers as well. It must be accessible, because if a farmer starts milking the cow in the morning in his stable, there's no consumer around typically, so it must be accessible in terms of data once being collected. And we have multiple object combination as well. Basically, we have 100,000 liters of milk, I think roughly per day in Switzerland. And out of them, we have those 20,000 producers coming into picture. So we basically start putting things partially together at larger dairy plants and then generate milk, which is not regionally labeled. And we end up in transformation, having that milk ending up in yogurt and cheese, what I mentioned before. So why I'm saying that? Because right here we have a business process which helps producers to produce high quality cheese and being regionally accessible. So they have a commercial unique selling points. And the consumers would be clearly interested in understanding, well, this is really Appenzeller cheese or St. Gallen milk at hand. For that, we need, of course, devices to help with the measurements. Typically, those devices are physical ones, which are sensors collecting volumes, collecting values of temperature, values for pressure and whatnot. And they help to interact with those internal and external ecosystems. And if they are now based on a blockchain-based model, we may have a chance of persisting data for a commercial process such that everybody participating in the system will have a chance of clearly tracking down where that piece of cheese came from, what he is at the moment using in his breakfast part. But IoT has some interesting side effects. We have to make sure that the power is efficiently used. So if there's sensors or temperatures, we cannot always plug them into a power supply. They have to run batteries. And they still have to make sure that data rates are supported at a suitable bandwidth. We have to probably have some long-range communication support and transaction patterns efficiency, because in every different stable, the cows are milked in different locations, and you cannot simply build up a large-scale sensor network, because that would be way too expensive. And that's why low subscription costs for data collections and communications between those devices is key for a situation where you want to have a tracking and tracing application at hand in agriculture's environment. That looks different in Industry 4.0 for sure, because if you have a construction yard for, let's say, car manufacturers at hand, there's power typically, there's energy, there's light, there's communications, etc. But take a look at the regular farm. There's basically nothing, maybe except for some 5G accessible information, but even that might not be perfect in some rural mountaineering areas. In addition to that, many of the devices we use are very restricted. They're not really machines we use for sharing our PowerPoint and running the webinar with Zoom. But we have just examples, Telos B nodes, Open nodes, Arduinos, or even sensors. And you see RAMs or flash sizes in terms of kilobytes are very small. And then sensors typically not really existing at all, only a few bytes are in place before they have to be communicated out there. That is the situation we faced, and why do we mention those ones now in the situation of commercialization and blockchains? Because I mentioned that the idea to have those physical devices collecting information, persisting that in a ledger such that producers and consumers can have access to the same information transparently, can be done. But the persisting of data, as I mentioned beforehand, in blockchains and distributed ledgers is different. It depends on the DL or the blockchain case, and what type of resources do we need for that if you run the hashes. That is a very limiting factor. So we looked into a whole bunch of different cryptographic functions, and mostly SH256 or 512 or the ED25519 signature generation algorithms were looked into, and we tried to sort of figure out by experimental measurements how many hashes we can generate per second HPS, while an Intel i7 CPU can roughly do 200,000 right here. A Telos B node can only do 30, 90 mega, 2560, 80, and the Raspberry Pi get close to 32,000 hashes per second. But if you take a look now to a public blockchain, like in Bitcoins, we need exa hashes per second. So these are just numbers which are a joke. So which clearly indicate that the use of blockchains for business processes in the IoT domain see some limitations. And if you go for even more advanced hashing algorithms, signature algorithms right here, then you see basically you cannot really use IoT infrastructure to bind them directly. And so we looked further to the resources which we need for blockchain functions in general. So you need to do some ordering, you do some mining, you have a full light node, which basically means in the full node, the full chain is maintained, a light node only the past couple of transactions are in place. So you cannot verify all the transactions which you might want to, and you can submit, of course, and verify transactions in the given chain if you're a node. And if you take a look at CPU memory storage and the network requirements at hand, CPU needs are basically very high, and for mining or full node operations, such devices I shown before, it's simply impossible. You have no chance to really do something about it. Memory-wise, nothing you can really do. You can submit a transaction, interestingly enough, because there is enough power to do that. And the storage is fine as well, because you have exactly the data being collected for, and then you run into very low network requirements because you just have the data, maybe header, and here goes. And that's why the submitting of transactions from a business process management perspective during the operations of that supply chain is the only thing a blockchain enabled process can support. It's submitting transactions in IoT. Otherwise, you have to collect things and then do them processing wise in some sort of decentralized, centralized combination and then push them out. But then, of course, the question is, do those initial statements of reliability and transparency really hold? Because between the sensor and this sort of node aggregating data, we do see very different potential attacks happening. So let me briefly now try to assess the blockchains and then trying to look into the business process management and blockchain pros and cons. If we just assess the blockchains as they stand right in there, including the smart contracts at hand, we see that there is a certain level of trust in the ledger's case on the nodes who write and run the consensus. And the public blockchains, it's just on the consensus mechanism. So basically on the cryptographic setting of algorithms we follow. So this SH256, for instance. So when people talk about the trustless chain, that is sort of weird because you trust exactly the cryptographic mechanism. And if you don't, the system will fail. But important is that there's typically no power to change or delete previously persisted blocks in that chain. No, again, in quotation marks, there is a likelihood that I randomly throw the dice and pick it and find something else, but it's like with any other key in the world. You can have a very low likelihood, astronomically low likelihood that this happens, but it's not a guarantee. That's important to mention. Secondly, those systems are fully decentralized, so nobody owns all the data. There's no single instance, and that's very different to the database we've seen beforehand. That's why the distribution of the blockchain helps for those economically driven processes where multiple stakeholders interact. And still, it's immutable, and we typically don't have a single point of failure. If a single node fails, all the others may still not been running, so we still can run that service as needed. What is the integrity question? Well, go back to the cryptographic argument in the very first part. Privacy depends on handling of the blocks and transactions content. So whenever I persist something in there, the integrity of the chain is guaranteed. But we all know if a sensor censors something which is not good, then we see the situation crab in, crab out. So the blockchain works nicely, but the input data was not nice. So that's what we have to take into account, especially where sensors are in place. Sustainability for the overall operation, I think not only for blockchains and ledgers, but for any business process management becomes very important. How many energy do we need to run such a system? They depend clearly on the consensus mechanism itself. Thus, a blockchain or distributed ledger with the different consensus mechanisms determines what we can do. And last but not least, the legal elements becomes important when we look at this code and the general contracts, which might not be a contractual part. But these are purely blockchains and smart contracts assessments with a few indications where business processes, commercial processes can benefit from and may see limitations. That's what I want to sort of discuss right here at this very moment as well, looking at our pros and cons. Now I would ask again into the crowd of the hall, if there would be a hall here in the webinar situation, what's the following? Some of you who sort of looked into that type of environment probably will realize that there is that's easily said, that's a string, obviously. Obviously it's an ASCII string, but it starts with a 1B, and that gives a very clear indication because that's the Bitcoin address in the pay-to-pub key hash format, which is a electronically generated, and that's important, uniquely generated address if you know what the public key of a public-private key pair is, because you use the public part of the key, run the SHA-256 algorithm on top of that, and then run WriteMed 160 out of that, and so you end up with exactly those bits at the end. So this is all electronic. It's driven by an algorithm. You can do that, I can do that, Giovanni can do that. Everybody can do that. We come to exact same output when we all know this public part of the key. And public parts of the key can be shared by definition because that's the term. So what's the following right here? It looks obviously like a sequence of strings as well, or one string as well of characters. In this case, it's probably only A, B, E, F, so it's not the full alphabet hand. Exactly, that's not the full one. So this is the 256-bit private key of some of us who owns most likely a physical asset, which is the top floor apartment at Canal and Gießen in Zurich. This is the place where you overlook the Zurich Lake. So you basically see those mountains as in my virtual background when you open up in the morning the balcony's doors. So the most important and very expensive place. Well, obviously private keys should not really be published, but here I wanted to show that because how can someone guarantee that this public part of the private key is attached immutably to that apartment on the top floor? There's no algorithm. There's no well-defined mathematical approach. You just have to have some external trust to whoever that might be can generate a public-private key pair, and you assign that to that specific physical objects. And that's what I want to make very, very clear at that moment. If we do use public-private key pairs and thus who owns what relationship in an electronically digitized representation format, which needs to be attached to a physical object, here the apartment, or a diamond, or 10 kilograms of gold in a single bar, if that's not too heavy, then we have already at that point this initial potential failure probability, like in the sensors. And that's exactly one of the issues when commercial processes rely on blockchains and you have no chance of generating all the data electronically, you might collect wrong information. And that's very important to consider, because everything else you build on top of that, you know that wrong input and everything else afterwards is potentially wrong as well. So if we take those 4 different chains we have looked into and look into transparency, control, reliability, and performance, at hand, we do see very many different situations. Transparency-wise, of course, from the world visibility, that's blockchain, to the role-based visibility. On the control, on public permissionless blockchains, there is an election process. Everybody can be elected and being placed into that minor section. In the private world, that's not the case. And what about reliability? Well, in a fully decentralized system, we have a full replication out there. So everybody can hold every data. I think at the moment we talk in the Bitcoin case roughly 290 gigabyte, which is not really that much, although it's growing over time. In the private permission one, we have only full or partial replication depending on the master-slave model we have at hand. What is important for business process management situation is, besides those characteristics, the usability in a given situation, performance-wise. How many transactions can we do if we have a commercial process which utilizes a chain? In the public case, it is quite slow because the consensus finding takes some time, and the replication models behind there need to make sure that all participating nodes have exactly the same view of that new state. And that's why in proof of work, we have high security, but it's slow to come up with a conclusive answer. And that's roughly in Bitcoin case, I think we're talking 7 transactions per second at most maximum. On the other hand, if you have a private permission one, it's a distributed ledger where we know the nodes, we can run a bicentennial fault tolerance mechanism, and you can go up to a couple tenth of thousands persisted entries of blocks inside the part. I think the fastest one at the moment gives you 600,000 transactions per second. But note, if you have this performance difference at hand, here you can easily do whatever you want to, but you have to trust the nodes to do the right. Here, you are much slower, but you do not have to trust anybody. You can basically prove afterwards that something went right or wrong at that case. If you compare the databases to the blockchains, the top 4 elements address the operations, the lower ones, the characteristics. I will not run through each of them in detail, but just probably picking up a few examples in here, especially the invariance, because we haven't talked about that. In blockchain case, the invariance for the operations is that any node can validate transactions. And that's very important to know, because in databases, it's a database manager who is in charge of the validation. Of course, physically, it might be 2 people or 3 people because you have technicians who have all the authorities to do so. But it's still a very much more centralized situation. And in that sense, the trust of a business process management based on a centralized model is possible. It's used in many systems out in the world, but it's very different compared to the blockchain situation. And in terms of characteristics, clearly the disintermediation is the key. While the public blockchain is fully reach out, the partial reach out private blockchain, the ledgers are more limited. In a central viewpoint, of course, we have a physical distribution, which is always possible logically. It's still in one database. Important is, what does our storage size do with that? In the blockchain case, we have n copies of the full chain, and typically those chains do not carry megabytes of data. In a few cases, we can only store a few bytes, not even kilobytes, only a few bytes per transaction, which basically means that for business transactions, you would like to run a limitation to, let's say, to 46 bytes per transaction is probably a clear obstacle. On the other hand, storage size-wise on databases, we can have whatever number of terabytes or exabytes out there. The larger ones is really much, much more important for larger data to be stored. In terms of history, we do have exactly this sort of storage size relation. The very positive side effect of the blockchain is that you can always fully achieve the entire history of the full chain from its very, very first statement being done. So whenever you have a transaction being persisted, it will remain. You have access to that. In a database, historic information is not necessarily there because you can overwrite an entry, you can delete an entry, and if the archival functionality is not taken on or instantiated initially, you have no chance. The data will be lost. And that's why the archiving function is only used in critical elements where you really want to have a full-fledged auditability, traceability at hand, because it might generate millions of additional sets of information to be stored. So it will explode in the size very, very quickly. So what does that mean now for our situation of blockchain benefits in our business process management relations or commercial processes in general? We have seen that trust is derived from the network's protocol transparency, so the blockchain itself, the cryptographic mechanisms at hand, and only those ensure that the blocks are immutable. And every single transaction is that moment attached to that trust. If somebody would verify that SHA-256 at this moment now would be broken, the entire blockchain would collapse right away. And all parties have access to a single shared copy, which is an interesting part because we have the same view on a distributed state. And this is for distributed systems people, I think, the regular situation. For commercial processes, that's not very often the case because you have many hierarchically organized companies where you have a single decision taker and everything moves along. There's no need to consult or consolidate or find consensus. Here in the blockchain case, we have that single copy, but it's out there in multiple instances and it cannot be falsified in that sense. So even you have the control of that, it might not be able to have a chance of deleting things, and that's good. So that's quite useful for commercial processes. Secondly, personal, persistent, digital, and ID ownership enabled characteristics are out there because we can support licensing of those information being owned. Much higher security, better cost efficiency, optimized reconciliation processes, wonderful. So that's very valuable for commercial processes at hand. Thirdly, cost reductions become very clear because there's automation, as I mentioned, there's optimization, as I mentioned, by getting rid of intermediaries, getting rid of third parties, is meaning that you have a cost reduction in place. So it's wonderful in that sense. So it's inevitable because we all know we are under cost pressure these days. The problem, though, is if everything like that would be put into the picture, we cannot come to a conclusive answer. Because if we run measurements in a blockchain system, we have decentralized collection of data at hand. But the gap of the correctness I mentioned beforehand, especially in IoT-based situations, is still there. So that gap is unsolvable. I was talking to the Ethereum founder, Vitalik Buterin, about that situation, and he mentioned to me it's unsolvable because we have to make sure that the sensors are calibrated, they're verified, they're signed, they're trusted. And we all know that trusted web shop as an example of a sort of marketing situation. If sensors shall be placed as an input stream into commercial processes, they have to have that verification at hand. And we all know that we can fiddle around with that. And it's very difficult to check from here a sensor being placed in whatever cacao plantation in South America. You cannot simply go there. An electronic verification of a Bitcoin, which was double spent, you at every point in the world have a chance to verify that it was double spending, yes or no. Improvement-wise, we can take many local decisions based on data which are secured, which are immutably available, and you can verify even later on that those improvements were done correctly. But they are limited in size, as we've seen. The storage space is very limited, so you have to very precisely define what you want. But to a certain sense, probably it's more a benefit than a drawback. Those decisions are time-stamped. So whatever you did in terms of improvements, you may have to think when to be done. Otherwise, it may come too late or it come too early. So you could be auditable, traced in there. So that's probably depending on the application-specific needs what to be done. Optimization-wise, we've seen that. The full chain can be optimized across all the BPM steps we've seen. All the stakeholders' activities are publicly visible if we have the blockchain hand. With limited visibility in case of distributed ledgers, we may have this consortium or enterprise-grade part as well. This is considered to be a drawback if you want to be fully transparent. This is considered to be the benefit if you want to have full control of the system. As well, you see, pros and cons are not clearly distinguished all the times. In automation-ways, the disintermediation is wonderful because we have a fully decentralized, automated, typically smart contract-based decision possibility at hand. On the other hand, complex decisions based on smart contracts, which are just more than a few lines of code, are getting very expensive because smart contracts are not being processed for free in a given situation. They require in Ethereum, for instance, gas, so you pay for them. And if you have a large if then else or case study, whatever not situation, they become sort of hard to be paid for. So the commercial usability most likely is limited, but again, it depends a bit on the given application. So what are the general observations? We do see that a blockchain helps to support distributed applications, but at a larger coordination effort, and the business process on top of that have to take care of that one. We have seen that the cost-benefit perspective is key for blockchains. These are the incentives. We have known costs in advance, hardware, the VMs, network setup, whatever the fees we have to pay. But there are sometimes more soft factors on the beneficial side. So the central infrastructure which we save, in contrast to the blockchain, are sort of very difficult to quantify in some cases. And once our risks are mitigated, our legal regulatory constraints are known, we may see applications which benefit from a blockchain because we have potentially a chance to see the addressing of value destruction problems. So once you have one of those assets out there, which is clearly linked to a physical or digital asset, then they cannot be destructed easily. You can always say there was the person who hold the last right to use it. And we have, unfortunately, many country-specific rules handling of those will become potentially obstacles because there is no internet law. Some rules in Switzerland may not apply in Spain, they may not apply in South America and vice versa. And so anything which runs across borders is on a legal side, especially when contracts come to the picture, a little bit more complicated. And last but not least, applications maintaining inherently digital assets do show a much larger description potential. So this media break type of thing is very helpful, but it needs always a circumvention beyond our pure situation. So let me conclude the talk as of today. We do see basically that blockchains are not really new. They show an illogical evolution of those linked lists with a cryptographic power attached to all those ones. They may exaggerate the processing demands, but this ensures immutability. So if there's a commercial process out there which needs a very high, I'm not saying 100%, a very high, 99.99% security based on those mechanisms we know, then proof of work is at this moment the only chance to go. The technical future of blockchains is based on those security ingredients of today's technology. In the long term, we see no clear indication where we want to go to. Just assume that quantum computing pops up and would make those hashing algorithms being obsolete and a sort of a very easy computational path. Then you could redo those hashes over time and change and fiddle around. And that moment, whatever had been stored in that chain will become wrong or potentially wrong. And this is clearly a problematic situation. But remember, this does not only affect our blockchains, it affects all IT today. How many systems in banking and finance use RSA-based signature schemes, encryption schemes? There is much more assets, much more value in there. So we will see not only a blockchain problem in that hand. And last but not least, the blockchain deployment for commercial business process management and commercial processes in general is limited because it's costly for full smart contract-based automation, and the size argument I gave is sort of tight. We cannot really store whatever we need to. And in general, we have to remind ourselves, why do we need, in some cases, a distribution of consensus? It does not always make sense. The case of the diary situation may make sense to a certain extent because consumers as well as producers are clearly distributed and decentralized. There are so many decentralized applications which do try to distribute the consensus, but could take a decision locally much, much easier. Thank you much for your attention, and I'm open for questions.
Okay, thank you very much, Burkhard, for your keynote. I think it was very, very informative and full of ideas, basically, to carry on the discussion. So I invite the audience to please ask questions. Nobody wants to break the ice.
There's so many open questions to look into, so I'm very happy to look into some of them.
Yeah, there's a question from Jan.
Your microphone's still muted.
So there was apparently some delay. I hope you can hear me.
Yes,
Yeah,
we can.
Great, thanks a lot. So I wonder, so you identified various challenges, I would say. You also referred to the case that in Switzerland you have been talking with the authorities. So what kind of role could the public administration play in regard to this technology? In how far could the state actually provide certain pieces of infrastructure, and how much would that be or would not be of value to the overall economy?
Yeah, that's a very interesting question, and we looked into that into multiple different facets. Let me start with the following statement first. There are countries in the world where the authorities are trusted by the majority, the vast majority of the populations. And there is countries in the world where basically nobody trusts in them, but they're instantiated. So these are very two different cases based on the initial trust assumption, where the outcome of the answer would be different, of course. But you mentioned the Swiss case, and so I can state that the trust into the authorities is very high, which basically means that potentially we could use, and this is now in the milk case as well, the example, something where all farmers have to register their cattle, and each cattle has at the ear mark with a unified number, etc., etc. So you could even trace and track at least parts of the meat until the cattle goes to the slaughter at that point in time. And here we discussed that with the federal government's experts, and Switzerland is way too small to have a blockchain-based solution work, because the trust in the system itself is so large that only local checkpointings would have to be done, and there is no need to run that in the blockchain-based model. There had been a project using Hyperledger in a distributed ledger fashion, where you can plug in certain modules, and that worked well. But the effort to be having such an infrastructure compared to a central database in Switzerland didn't seem to pay off, because that was, for the operational perspective, not perfectly well done. So in this case, I would say the authorities for that specific case mentioned clearly we don't have any advantage of having a blockchain-based solution, because we know everybody on the farming side, although it's a large number, but we have relations to them, there's no need. But I guess there are other cases in the world where that definitely looks different. And then you could have the authorities playing, let's say, a partial role of hosting a subset of activities, helping to represent a local set of producers, farmers, whatever that might be, and representing them against the outside world, if you need to sort of have a stable situation for external trading.
Okay. Any further question? I do have one, actually. I think that the comparison you presented, where you basically evaluated the various kind of blockchains, the various kind of blockchain consensus algorithm against several type of IoT devices. You mentioned, for instance, the Raspberry Pi or the Arduino. It's very valuable, because I've seen most of the research work in the literature just say, okay, just focus mostly on Ethereum or on Bitcoin, and they say proof of work is so convoluted and it requires so much computational power, it's not feasible to be performed on an IoT devices. In your work, you went further, basically, and you also analyzed the impact of other consensus mechanisms. You mentioned PBFT, for instance, or even proof of stake, and you basically came up in the table that even those consensus mechanisms that are typically less computational intensive, that proof of work still doesn't scale enough to be performed on an IoT device alone. And on that purpose, I was wondering if you've also taken into consideration when carrying out this analysis, the IOTA protocol, even though it's not technically a blockchain, is named to be a distributed hash graph. And what if so, do you have any insight on that? Because IOTA is, I mean, from their basically corporate website, they say that they aim at bridging the gap between IoT and blockchain as a mechanism.
Yes, indeed. Of course, we talked to the IOTA guys as well. It's very clear that their DAGs, they have this directed acyclic graphs, have a very different collection structure, and it's basically helping to identify in an IoT setting, of course, the variability of sensors, which might be mobile. So that is, it's definitely a very good situation. We didn't look into the evaluation in our devices because we decided on purpose to have the chained backward link list as the only thing without comparing apples with oranges. The situation is very different because you have a different data set, you have a different structure, you have different sizes at hand, and then comparing apples with oranges wouldn't have made sense in that. So we didn't look into that on purpose. But as you mentioned, we took the sort of consensus mechanisms on the traditional backward link list, the chain models at hand, because that sounded to our mind as a more reliable comparison being possible. It is of interest, and I agree on your statement right here, probably to find a dedicated model in which you can have those two elements being facing each other and saying in which cases they are better, the other ones, then in one case the auto better than the other blockchains or vice versa. We did, however, realize very quickly that whenever you start combining multiple mechanisms to form a reasonable functionality usable at the application layer, the number of combinations you get is so large that, again, you start comparing one instantiation of an application with another one, and that's probably not comparable. And IOTA, that will lead very quickly to that because you need different cryptographic functions in a combination which might run in a different order, in different sequence, on different nodes to be combined, and then it's very hard. So we decided not to do so because there wouldn't have been an outcome which you can place in a table which is sort of very strong by itself. It would have been just a random selection of numbers which you can argue for or against, and that's something we didn't want to do.
Yeah, I see. I perfectly see your point, and I think it's I mean, it makes even more valuable the analysis on that you carried out on that part. Thank you. Okay. No further questions. Okay, if not, then I will just just add another comment. I think also what it's interesting, on the earlier slide you presented the difference between blockchain, the classification of blockchain 3.0 and 4.0 you made, because typically I see that up to 2.0 everyone agrees. Basically 1.0 is Bitcoin, you just have to exchange cryptocurrency, and with the 2.0 you also add smart contract and the capability of distributed code execution in a safe way, I would say. Yeah. And it's interesting to see because in 3.0 I've heard, for instance, that somebody refers to 3.0 as the introduction of oracles, so of bridging basically the gap between the on-chain and the off-chain world, and they mark that as a 3.0 milestone. Whereas on your comparison, I saw that you were more focused on the application scenarios for the business. So in that case, the first two were more on the basically crypto market, and in 3.0 you mentioned application, and 4.0 is where it actually scales to other markets, which are not the private. I mean, it's not just the financial one or the crypto one. So it's also interesting to see those different perspectives.
Yeah, that's interesting that you mentioned that. We had one sort of reason why we did it this way, because on-chain and off-chain sounds to us as a very clear functional internality of a blockchain or ledger, like the consensus mechanism. And in our eras being distinguished, the consensus mechanism doesn't show up either. It's nothing which the application by itself is really worried about, because they just need an immutable ledger, full stop. And that's why we didn't want to sort of export internal technicalities into the world. And in our 3.0 situation, the decentralized apps are the ones which then distinguish themselves on what type of application they want to do, but not really by changing the underlying system. And then the 4.0 with the ecosystem in hand is building the entirety of external functions around it to make sure that a chain is just available as a service, maybe, although I doubt that this is the good term. I've seen it a couple times, but I believe a blockchain as a service is not really good. Otherwise, it's a distributed ledger as a service, but not a blockchain based on our definition.
Yeah, definitely. Okay, then thank you very much for your keynote and for the discussion, Burkhard. And I would then move to the closing session of this of the blockchain forum now.
Thank you very much to Giovanni, you, and inviting me, and thanks to the audience for listening, although I have not seen anybody of you, but thanks a lot.
Okay. Just 1 second, I will share my screen. Okay. Okay, so to wrap up this to wrap up today's session, we have heard of several very interesting, in my opinion, research topics. And if I had to sum them up on 3 main, I would say, research line, I would say that the ones were basically could be summarized into trust patterns, the impact on modeling for the selection and the creation of blockchain solution, of blockchain-based solutions. And in particular, I've seen that the majority of your presentation dealt with the problems related to Oracle and how to implement them and how to create effective patterns to ensure that we do have reliable and timely information from the outside world. This is very interesting because last year, when the blockchain forum was carried out, we found together with the audience the following 6 research questions that the audience deemed to be relevant for the next 5 years, which are confidentiality and privacy, integration and interoperability, analysis and mining, legal aspects, and the adoption and success factors, blockchain solutions, and the verification stuff. So, for instance, verifying that smart contracts do what they aim at doing. It's interesting because based on the presentation of today's sessions, I would say that the integration and interoperability questions and the adoption and success factors question were both tackled by your work. Instead, the other research questions still remain valid, I would say, or at least they, based on this, of course, only on the subset which was presented today, there's still open questions that nobody, deep dived into. And to do the same, Paul, for this year, I basically asked during these sessions to collect on Whova, your impression on the next research questions that we can find in 2020. And besides, and I would say that confidentiality and privacy, integration and interoperability analysis and mining were reconfirmed by your responses by your answers in the poll. I deliberately haven't shown you the one that we defined in the previous year to see if some of you still found some of them valid. And for those of you, you all mentioned those one. You also nobody actually mentioned the legal aspects and the adoption and success factors. So we can evaluate if we still think those are research questions worth investigating. And also we have new entries. In particular, some you had the modeling and design patterns. Some of you suggested as a challenge how to define patterns and how to model actually smart contracts and the behavior of the blockchain. We have also security aspects, which I think they are worth to be distinguished between the integration and interoperability, from the confidentiality and privacy ones, because typically privacy is about sharing data. Security is more on, are there any vulnerabilities that can be exploited, for instance, in the consensus mechanisms, in the way the hashes are computed, and yeah, assessing the security aspects is definitely a topic that could be worth investigating. And the final one is also to provide flexibility, because as we know, the blockchain is typically relies on a persistent, immutable ledger. We also have the problem of forking, for instance, when we do have a change to have a change in the consensus mechanisms, and everybody must agree on that part. Therefore, those were the topics that emerged from the poll that we carried out during the session. And as a final task, I would kindly ask the audience to please participate in a poll. You should, I will provide you a link to an open questionnaire that you can fill in right now, and to actually see which are, in your opinion, the most relevant research questions in 2020. You can choose multiple options, and you can access the questionnaire also by scanning the QR code I show here. Anyway, just a sec, I will provide you the, I will provide you in the chat the link to the forum, to the questionnaire. Just one sec, sorry. Okay, you should be able to answer this questionnaire just as a last part. I will also show you the QR code so you can scan it, and I will give you just a couple of minutes to perform the poll. Okay, I see some of you are already answering. I'll give you just 1 minute more. Yeah, and in the meanwhile, I can show you the results. So now we do have the integration and interoperability and the modeling and design patterns questions as the top ones. And then we do have basically confidentiality and privacy and legal aspects still considered quite relevant, I would say. We also have the growth in the security and in the flexibility and in how to ensure flexibility. Let's see if we do have some other updates. Okay, I think that it's also 15, it's also 3 p.m. So I think we can close the poll right now. And yeah, I feel, as we did during the last edition, we will also carry out this poll on the next year. So to see if some of the few new papers will actually tackle those research questions we identified, and also to find if there are new questions that rise during the year. Okay, I think then we can now conclude this session and the blockchain forum. I would like to really thank all the participants and the speakers and all the speakers for participating in this event. I think it was despite all the issue we had on the coronavirus, on having to do that remotely and not in person, I think it was really a really interesting occasion to meet each other, and to basically draw inspiration from each other's work. So I would really like to thank you so much for making this edition of the Blockchain Forum be, I would say, a success. Thank you very much. Thank you very much for everyone, to everyone. Okay, and of course, see you next time in Rome.